Hi students, today we're starting a new chapter on theorems of circles. So theorems about circles. 14.1 is about tangents. If we were doing this in the classroom, and in fact we may do some of this, we would do some more constructions involving tangents and circles to explore this. For this video, we're going to be a little bit more efficient and we're going to hone in on what the actual theorems are and then how to apply them. Okay, 12.1 tangent lines, theorems about circles. Okay, some vocabulary that you need to know are going to be point of tangency, and then also what it means for something to be tangent to a circle. The point of tangency is the point where a circle and a tangent intersect. Pretty straightforward. What does it mean to be tangent to a circle? A line in the plane of the circle that intersects the circle in exactly one point is a tangent. So the point of tangency is the point where a tangent and a circle, in this case, intersect. A point of tangency, in other instances, there are other times you have points of tangencies besides circles, especially as you get into graphing in Algebra 2, and then in pre-calculus, and finally calculus, there'll be a lot about tangents. And tangents can be, lines can be tangent to other things besides circles, such as if you think about a parabola, remember a parabola, U like this? I can also have a line that is tangent to that at one point. But in this case, what we're interested in are circles. And it is possible to have a line that intersects a circle at one point. And that would be the point of tangency. Okay, and that's the tangent line. Okay. Now, one of the things that is important to note here is that the radius of a circle also, of course, intersects the tangent line, because the radius is defined as that segment that has its endpoint at the center of the circle and on the circle, right? So, interesting thing about a tangent and a radius is that where they intersect makes a right angle. So, a tangent, so this is a theorem, a tangent is perpendicular to the radius. Or if we wanted to make that into an if-then statement, if a line is tangent to a circle, then the line is perpendicular to the radius. At that point. Oops, there we go. So if a line is tangent to a circle, it is perpendicular at the point of tangency. So if we have a circle O, and we draw its radius, and we also draw its tangent, which I did not do a perfect job of drawing there because it actually goes there in multiple places. This is our point of tangency. And those two lines are going to be perpendicular. So this is A, B, This is P. So another way of saying this is if AB is tangent to circle O, then OP is perpendicular to AB. Okay, in this case, the converse is actually true. Do you remember what the converse is? Converse is when you switch the if and the then, when you change it around. So the other thing that we happen to know is anytime you draw a line that is perpendicular to the radius of a circle, it has to be the tangent. Now, Euclid likes to present these as proposals, and Euclid would say, okay, let's say that AB is perpendicular to OP, the radius of a circle. I propose that it is a tangent, and we've already defined tangent. And so then you go through the possible constructions and you see if it's possible to construct a tangent that is perpendicular to OP. We've done some things like that in class where I've asked you to try to do something that's impossible. That's a proof by contradiction. You try to do something and then you determine it isn't possible, and then you can see, okay, what I have proposed to be true is true. So if a line is perpendicular, now what else? Not just perpendicular, but also it only touches it can't be just perpendicular to the radius at any point, right? Because if it's perpendicular to the radius going through the middle here, that's not a tangent. It has to be perpendicular at the endpoint. So if a line is perpendicular to a radius at its endpoint on the circle, then the line is tangent to the circle. So in other words, looking at our circle above, if AB is perpendicular to OP at P, then AB is tangent to circle O. Okay, another theorem. So what if we have two tangents coming from the same point to a circle? What would that look like? So here we have our circle. I don't know why I'm doing this freehand. I could be using my compass. I may do that for the next one. And I pick a point out here, and then I draw the tangents. Okay, so if two tangent segments to a circle share a common endpoint outside the circle, then the two segments are congruent. So if two tangents share a common endpoint, in other words, they intersect if they're lines, right? Outside the circle, then the two segments. I'm going to call these tangent segments to clarify that we're not talking about lines. Then the segments are congruent. So in this case, if BA and BC are tangent to O, then BA is congruent to BC. Okay. Also, tangents have special relationships to angles inside of circles. Let's take a look at the special types of angle relationships we can find. So this is in problem 1. We're going to look at angle measures. So if I take a circle, let's see, I only have a pencil on my compass right now. So we're going to see if that will show up on here. I think my free-handed circle was better. Okay. Okay, here's our circle. Here is our point outside the circle, and we're going to have two tangents again to our circle. When drawing tangents to circles, sketching even in your notes, I recommend using a straight edge. It is very hard to freehand tangents well. Okay, M, L, N. If you're following along in your book, you'll see I did my tangent on the opposite side of the tangent in the book. So okay, we know that this is 117 degrees, and it wants us to find, okay, what's the value of x? Now, what information do we have here? Okay, well, first of all, we have a quadrilateral, right? There's a quadrilateral here. And we have one angle in that quadrilateral. Quadrilateral, oh, we should name this circle O. We have a quadrilateral M, L, O, N, right? And quadrilaterals have a total angle, the sum of their angles is 360 degrees. So if this is 117 degrees, and what do we know about the radius and a tangent? Those make right angles. So we know that each of these is 90 degrees, right? Well, so we know that the measure of angle M plus the measure of angle L plus the measure of angle O plus the measure of angle N has to equal 360. Substituting in, we know the measure of angle M, which is also x, right, plus 90 degrees plus 117 degrees plus 90 degrees equals 360. So then our measure of angle M has to equal 360 minus 297, which is going to be equal to 63 degrees. Okay, now every time you have a central angle, because remember this is our central angle, and you want to find the angle on the outside of the tangent, you're always going to have a quadrilateral where we know that two of the angles in that quadrilateral are 90 degrees, so they add up to 180. So because they always add up to 180, 360 minus 180 leaves 180 degrees for both of these two angles. So we can say that the central angle plus the tangent angle has to be equal to 180 degrees. Or in this case, the measure of angle M, or the measure of angle O, we'll start there, plus the measure of angle M equals 180. So you can work it out using the entire quadrilateral, or you can know that these two angles that are opposite each other have to be equal to 180. They are supplementary. So those angles are supplementary. The angle formed by two tangents with a shared endpoint. I may run out of room. Outside the circle and the opposite central angle are supplementary. That's another theorem. Okay. Problem 2, finding distance. So real world application. In earth science, the CN Tower in Toronto, Canada has an observation deck 447 meters above ground level. About how far from the observation deck is it to the horizon? So the horizon and the top of the observation deck form a tangent line, those 2 points. So we're going to make a sketch, and we're going to use the radius of the Earth as being 6,400 kilometers to help us with this. Okay. So we've got the Earth, and then we've got this observation tower, and we have a tangent coming from that. Okay, this is 6,400 kilometers. And then this is 447 meters. And do we know, what else do we know? Well, we also know that this is 6,400 kilometers. Now, and this is what we're solving for right here. Notice that this is a right triangle. So if we have a right triangle, how can we solve for this? This is T, E, and C. Okay. Well, we know that ET squared plus EC squared has to be equal to TC squared. Okay, so ET is X, so X squared plus EC. EC is 6,400 squared, okay, equals, all right, how am I going to find TC? This is in kilometers and this is in meters, so I need to do a conversion. I need to convert this to kilometers. So this is the same thing as if I have meters and I want kilometers, I move 3 decimal points to the left. 1, 2, 3. So it's 0.447 kilometers. So this is going to be equal to 6,400.447 kilometers. Okay, putting this in the calculator. This is definitely a calculator problem. We have, I'm going to actually move this around first. X squared equals 6,400.447 squared minus 6,400 squared. So I've got 6,400.447 squared minus 6,400 squared. That is equal to 5,721.80. Take the square root of that, so I can put in square root up, enter, and I get 75.643 kilometers. And this problem wants me to find the answer. It just says about. So I think we could probably just round this to the nearest kilometer. So this is approximately 76 kilometers. Okay, so in word problems like this, it's important to be able to, even if they don't give you a picture, to think about what are the relationships going on in this circle that gives me something I can work with. So one thing you can definitely work with are right triangles. So you want to try and see, okay, do I have a right triangle that I can form with my tangent line? Another thing that you know about are central angles and the angles formed by tangents. When they're opposite each other, they're supplementary. So you can look for that relationship as well. And then also tangents from the same point, external to the circle, are equal to each other. You want to look for those relationships. Okay, problem number 3, finding a radius. Okay. Problem number 3, we are given a tangent and then a secant, which we haven't talked about, but the line for AC, the secant, and we need to find that radius. So we'll draw a sketch. This is circle C. And we have this point right here. So if we know that this is 12, and we know that this is 8, how can we find the radius of this? So now in the book, it gives you more in the picture to start off with, but I want you to get used to the idea of seeing a tangent and knowing that you can draw the radius. So we're going to start there. So AB is tangent to circle C. Find the radius of circle C. Okay, well, the first thing I'm going to do is I'm going to draw in this radius. And I'm going to note that that's perpendicular. And then this is also a radius. So we've got X here. I want to find that radius. This is also X. Now I've got another right triangle. This one's going to take a little bit more doing because we're definitely going to end up with some x squareds and something we have to factor. But we know, because this is a right triangle, that AB squared plus BC squared is equal to AC squared. And we're going to substitute in. AB is 12. BC is x. And AC is x plus 8. So 144 plus x squared equals x squared plus 16x plus 64. If you don't remember how to FOIL, you need to go back and review that. Okay, if we simplify very nicely, our x squareds cancel out. That's very helpful in this problem. And we subtract 64, and we end up with 80 equals 16x. And so x is going to be equal to 80 divided by 16 is 5. So our radius is 5. We weren't given any units for this, so that's our answer. Okay, next problem. Is ML tangent to N at L, and explain why. So we're given these values. We're going to make a sketch of this. We have the segment from M to the center is 25. We have a radius of 7, and we have a tangent length of 24. How could we determine if that line was actually a tangent? So we don't know it's a tangent, but it looks like it. Problem 4. Okay, so we have circle N. We have a point M. Okay, and the values that we have are 25, 7, and 24. Now, we need a letter there, L. So, is LM tangent to circle N? So, if angle L is a right angle, then I think we can say that yes, LM is tangent to circle N. Because remember, that means that the radius is perpendicular to this segment, which means it would have to be a tangent. So we want to know, is that a right angle? Well, if it's a right angle, then the Pythagorean theorem holds. And we could say, okay, does NL squared plus LM squared equal NM squared? Well, let's find out. NL is 7. LM is 24. And NM is 25. Well, this is 49. What's 24 squared? 24 squared is 576. 25 squared is 625. So does 49 plus 576 equal 625? Yes, it does. So, yes, we can conclude that LM is tangent to circle N. Okay, one more example problem for this lesson. Problem 5. Problem 5 is a fun one because it is a circle inscribed in a triangle, but this triangle is made up of tangent segments, okay? So let us sketch this. Okay. This can be a challenge to sketch. Okay, this is 15. This is 10. And this is 8. So what's the perimeter of ABC? Well, because this circle is inscribed, we know that inscribed means it touches at one point. So these are our points of tangency. Okay, and if we have points of tangency, that means we have congruent tangents. These two tangents come from B, so they have to be equal to each other. These two tangents come from C, so they have to be equal to each other. And these two tangents come from A, so they have to be equal, which means that this has to be 10, this has to be 8, and this has to be 15. Which means that our perimeter is going to be equal to 2 times 10 plus 2 times 15 plus 2 times 8. 20 plus 30 plus 16 is 66 centimeters. Oh, you can't see that work. I'm sorry. There. 2 times 10, 2 times 15, 2 times 8 is equal to 66 centimeters. Okay, homework for this unit looks a lot like the practice problems we've been doing. You may be asked to figure out some angles that we didn't practice in class, but if so, know that we have at least talked about what you need to do. Either you need to look for those central angles or you need to look for right triangles. And the same thing throughout here. You either need to be using the fact that you know that tangents from the same point are congruent, or that you can form right triangles and use the Pythagorean theorem for any of these problems. Okay, enjoy your homework. Know that I am available in class to answer questions, and I will see you next time.